Good morning. My name is Pretorius, and my project entailed an investigation into the effects of implementing a spiked nose attachment in shockwave reduction around the body. When an aircraft travels at supersonic speeds, the concept of shockwave generation is of immense importance. Where there is a large angle of air deflection present, large pressure waves are generated and undergo constructive interference, resulting in a large pressure wave known as a shockwave. This loud bang, known as a sonic boom, is what you hear when witnessing supersonic speed. It is due to this phenomenon that supersonic travel is banned over land in the USA and in Europe. As a result, it is required to conduct an investigation into the reduction characteristics as a result of the implementation of a spiked nose attachment. The purpose of this investigation is to develop a spiked nose attachment that will significantly reduce the magnitude of the shock wave generated at supersonic speed. The main points that will be focused on are the magnitude of the shock wave and the magnitude of the drag coefficient of the respective configurations. To successfully conduct an investigation into this concept, it was necessary to fully understand what needed to be done, and from this a method was obtained to complete the investigation. Firstly, an in-depth understanding of supersonic flow around the body is obtained. Following this, the geometry which is to be used as the baseline body is acquired. When conducting CFD simulations, it is necessary to investigate the testing conditions required to accurately simulate the conditions under which the aircraft will be operating in reality. The next step is to investigate and develop a spiked nose attachment suited to this problem. When investigation is conducted, it is important to conduct a theoretical analysis of the system. The data obtained in the simulations will be compared to the theoretical data in order to validate the results obtained in the simulations. In this instance, the distance between the shock wave and the leading edge, the change in density and the change in pressure are all compared to validate the results. Various two-dimensional steady flow simulations are then set up for the basic spike geometry, followed by simulations for the newly proposed spike geometry. The different configurations are then simulated under the same operating conditions, at which point the data is validated and recorded. Once all the data is summarized, it is analyzed and compared to one another. Based on the results obtained in the analysis process, conclusions are drawn and recommendations are made on how to further develop this system. The testing conditions that apply to these simulations are that the simulation is said to be a steady-state two-dimensional flow simulation. The free stream velocity, temperature, and pressure are set to be Mach 2.5, 216.15 Kelvin, and 7,130 Pascal, respectively. In this case, air is assumed to be an ideal gas. The surface of the model is said to have no slip, no heat transfer, and the roughness constant is set to be 0.5. It is important to ensure consistent application of these testing conditions to enable accurate comparison between the different model simulations. The reference simulations were conducted to obtain the baseline to which the new spike results will be compared. The body without the implementation of any spike attachment was simulated first, followed by the body with the attachment of the basic spike shape. This configuration was simulated at 3 different lengths. It was concluded that the implementation of such an attachment significantly reduced the magnitude of the shock wave as well as the drag coefficient. The new spike geometry, as can be seen in the figure, possesses some diameter increments at an angle of 45 degrees at select locations. The length of the segments between these locations is as a percentage of the total length to enable accurate comparison between the different spike configurations only as a function of their lengths. This spike configuration is then also simulated at 3 different lengths. It is evident that at the increments, additional shock waves are generated, and the shock wave created at the second step actually results in constructive interference with the shock waves generated by the body. This shock wave, however, partially deflects the air over the body, resulting in a lower drag coefficient compared to the spike of basic geometry. To compare the performance of the respective spike attachments, Graphs are plotted showing the effect the two different spike geometries have on the measures of interest. The first is the effect of the drag coefficient. As can be seen in this graph, the longer spike attachment results in superior reduction capabilities. It is important to note that at some length, known as the critical length, the implementation of such a spike could actually be detrimental to the reduction abilities of these measures. It is also clear that the new spike geometry, portrayed by the orange line in the graph, performs better than the basic spike-shaped attachment for the reference simulations. The next point of interest is that of the shockwave reduction ability. This graph shows that again the longer spike attachment provides a high amount of reduction. The new spike, however, does not perform as well as the basic shaped spike in the reduction of the shockwave magnitude. As previously mentioned, this is due to the constructive interference that is present on the new spike geometry. The performance of the various spike attachments can be seen in this table, where the percentage reduction is shown for each configuration. The result of the body without attachment of any spike implementation is used as a reference point to obtain these values. After analyzing the relevant data, it can be concluded that the basic spike geometry reduced the drag coefficient and magnitude of the shockwave by approximately 38% and 7% respectively, whereas the new spike geometry reduced the same measures by approximately 39% but only 6.8% respectively. The shockwave reduction provided by the basic spike geometry is superior to that of the new spike due to the constructive interference present at the diameter increments. It is due to this that for purposes where higher efficiency is of greater importance, such as with fighter jets, one would implement the spike attachment of the new spike geometry. When it is necessary to further reduce the magnitude of the shockwave, such as with passenger aircraft, one would implement a basic spike geometry. Based on these conclusions, recommendations are made on how to further develop the design of the nose attachment. The recommendations are as follows. One can find the critical length of the spike at which optimal drag and shockwave reduction characteristics are achieved. One can increase the rate of change in diameter of the basic spike shape to obtain a larger diameter at the connecting point of the aircraft. This would result in less air being deflected of the body, which could reduce the magnitude of the shockwave as well as the drag coefficient. For the new spike geometry, one can find the optimal distance between the second step and the connecting points of the aircraft to allow partial air deflection over the body, keeping the drag coefficient at minimal, but to prevent constructive interference between the shockwave created by the second step and the shockwave created by the body. I would like to thank you for listening to my presentation on this topic. I hope you find it insightful and interesting. Thank you.